In this lecture I'll answer on two questions. In the first question, we find out the area of this rectangle ABCD that blocks this circle, and in the second question, we find out the area of this trapezoid ABCD. So we start with the first question. In the drawing, we have rectangle ABCD. Inside rectangle ABCD, we have this circle. This circle is inscribed by rectangle ABCD. This is called EF. This is equals to 12 units in its length. This is line segment FG. This is equals to 10 units. Again, our mission is to find out the area of this rectangle ABCD. So we define the width for this rectangle ABCD is AD. And the length from this rectangle ABCD is AB. And we know that the area of rectangle ABCD is equal to the length times the width. We define the point, the center of this circle. This point is point O. Point M is the point of tendency or tendency with this circle, and point N is the point of tendency or tangent AB with this circle. We define the radius of this circle is R, and we join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of this circle that is equal to R according to our definition. And because of the fact that the radius OM that is equal to R, the radius OM is drawn to point M, that is the point of tendency of tangent DC in the circle, and whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and M together by a straight line. ON is of course the radius of this circle that is equal to R. The radius ON that is equal to R is drawn to point N, that is the point of tendency of tangent AB with this circle. Whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the same rule, rule 1. Point E is the point of tendency of tangent DA with this circle. We join points O and E together by a straight line. OE is the radius of this circle is equal to R, and again the radius of E is drawn to point E, that is the point of tendency of tangent DA with this circle, and whenever your radius is drawn to the point of tendency, then tangent DA will be perpendicular to the radius EO. DA is perpendicular to EO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees, according to the same rule, rule 1. So by doing this construction, we created a quadrilateral DMOE. Inside this quadrilateral DMOE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of these 4 preceding angles, in total they must be equal to 360 degrees, according to the rule. It says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore these 4 preceding angles must be equal to 90 degrees in its size. So inside quadrilateral DMOE we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So related to this quadrilateral DMOE is a rectangle because it has 4 right angles. Okay, so actually we don't need this step. We just focus on the lower quadrilateral EO and A. In the lower quadrilateral EO and A, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces again. In total, they must be equal to 360 degrees, according to the same rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 pieces again must be equal to 90 degrees in its size. So the big angle MO1 is equal to 90 degrees plus 90 degrees, that is 180 degrees. So the big angle MON is equal to 180 degrees in its side. And we know that any angle that is equal to 180 degrees in its side is defined as a straight line. Therefore, line segment MON is a straight line. And if line segment MON is a straight line, then line segment MN is also a straight line. But MN is a straight line that touches the circle at 2 points M and N, and therefore MN is a chord it is a chord that passes through the center of the circle, that is to say for this point O, and you know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, MN is the diameter of the circle. So I write it down. MN is a chord that passes through the center of the circle. therefore Mn is the diameter of the circle. So Mn is the diameter of the circle. And dA is the width. So you can write down that dA is the width of rectangle ABCD. Mn is the diameter, it is a straight line. Therefore, this shape DM and A consists of 4 sides. 1, 2, 3, 4. And therefore it is a quadrilateral that has 4 right angles. And you know that any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral DMNA is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DMNA, side MN must be equal to the opposite side DA. Okay, so I think here that MN is equal to DA, according to the rule that the opposite sides of a rectangle are equal to each other. So in the next step, we will extend the radius EO by straight line until it touches the circle. And we will define the touching point of the extended radius EO with this circle. This point is point L. So EO is a radius, it is absolutely a straight line. When you extend the straight line EO by straight line, the result is EL. When you extend the straight line by straight line, the result must be a straight line. Therefore, EL is also a straight line that touches the circle at 2 points E and L. So, therefore, EL is a chord, EL is a chord that passes through point O. Why EL passes through point O? Because we extended the radius EO by straight line. Therefore, EL passes through point O, that is the center of the circle. So chord EL passes through the center of the circle. Therefore, EL must be the diameter of the circle. Any chord that passes through the center of the circle must be the diameter of the circle. EL is the diameter of the circle. We already found out that MN is the diameter of the circle. Again, the diameter of the circle is equal to MN. MN equals to DA, and DA is the width of rectangle ABCD. But we just like now found out that EL is also the diameter of the circle. Write it down, EL is the diameter of the circle. You can write here in the long equation that EL is the diameter of the circle. EL is the diameter of the circle, and from this long equation EL equals to the diameter equals to MN equals to DA equals to the width of rectangle ABCD, we will derive that the width, that EL equals to the width of rectangle ABCD. EL equals to the width of rectangle ABCD. In the next step, we will join points F and M together by straight line. By joining points F and M, we created them peripheral angle EFL. This is peripheral angle EFL that subtends on EL, that is the diameter of the circle, and we know that any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size according to rule 7. So I repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing, we have a circle. We know that AB is the diameter of the circle. This is peripheral angle ACB that subtends on AB, that is the diameter of the circle. And therefore peripheral angle ACB must be equal to 90 degrees in its size. So as I mentioned before, we can implement rule 7 in our drawing. Like in our drawing, we have peripheral angle LF3 that subtends on EL, that is the diameter of the circle, and therefore according to rule 7, peripheral angle LF3 must be equal to 90 degrees in its size. In the next step, we define this angle as alpha. That is to say, angle ELEF equals to alpha according to our definition. So in the right angle LEF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we will extend the diameter EL until it touches side CB of rectangle ABCD. You will find the touching point of the extended diameter here with side CB of rectangle ABCD. This point is point T. By doing this construction, we created there the big quadrilateral ETBA. Inside this big quadrilateral ETBA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this surface angle, in total the must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this surface angle must be equal to 90 degrees in its size. So inside the big quadrilateral ETBA, we have 4 angles, And according to rule 5, any quadrilateral that has 4 right angles must be at least rectangle if not a square. So, relate to the big quadrilateral ETBA, it's a rectangle because it has 4 right angles. So, write it down. Quadrilateral ETBA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ETBA, side ET must be equal to the opposite side AB. So write it down. In the big rectangle ETBA, side ET must be equal to the opposite side AB. Rectangle ETBA. Side ET must be equal to the opposite side AB. But according to our definition, AB is the length of rectangle ABCD. So can I agree that AB is the length? And from this equation, ET equals to AB equals to the length. We derive that ET is also the length of rectangle ABCD. ET is the length of rectangle ABCD. So in conclusion, we shall find out that EL is the width of rectangle ABCD and ET is the length. Okay? So, in the next step, we'll focus on the big right angle ETB. The big right angle ETB, this angle equals to alpha, this angle equals to 90 degrees, therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. So it is very easy to see that the big right angle ETG, is similar to the small right angle ELF according to angle similarity rule. That is to say, this is angle E that is also defined as alpha. Angle E is a common angle that belongs to both triangles. Angle E belongs to the small right triangle ELF, and angle E definitely belongs to the big right triangle ETG. So can I know that angle E is a common angle that belongs to both triangles? Okay? Angle E equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you found out that all the three angles of the big right triangle ETG are correspondingly equal to all the three angles of the small right triangle ELF. And therefore, those two right angles are similar to each other according to angle similarity rule. So I write it down. If we found out that the big right angle ETG is similar, this is the sign of similar, to the right small triangle ELF, according to angle similarity rule. And for the fact that those two right angles are similar to each other, We will derive that the following relationship exists between their sides. We will derive that side ET of the big right triangle ETB, of the big right triangle ETG, side ET of the big right triangle ETG, over side E, over side EF of the small right triangle EFL, is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. Working again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. ET is the missing side, so we leave it as it is, over EF. EF equals to 12 units in its length according to what is given us in the question. And it is equal to EG. EG in total equals to 12 plus 10, that is 22. Over EL. EL is the missing side, so leave it as it is. So in total, we should find out that ET over 12 equals to 22 over EL. Here we'll cross multiply this equation, and we will get that ET times EL is equal to 22 times 12. Again, we found out that ET times EL equals to 22 times 12. 22 times 12 is 264, so write it down. So we found out in total that ET times EL is equal to 264. But we already found out that ET is the length of our ABCD and EL is the width. So we substitute ET by the length and EL by the width. So in total we should find out that the length of rectangle ABCD times the width is equal to 264. But the length times the width is the area of rectangle ABCD. That is the area that we are looking for in this question. So if we find out that the area of rectangle ABCD is equal to 264 square units. That is the answer to the first question. Repeat again, we should find out that the area of this rectangle ABCD is equal to 264 units. So we finish with the first question. In the next step, I present to you the second question and we solve the second question of this section. in the second question, our mission, our task, is to find out the area of this trapezoid ABCD. It is given us in the question that line 7BQ equals to 4 units in its length, line 7QC equals to 9 units in its length, side AB equals to side AP, and line 7PD is equal to side DC of this trapezoid ABCD. Again, our mission is to find out the area of this trapezoid ABCD. So, AB is equal to AP. So, if we define the length of side AB as A, then the length of side AP also equal to A because they are equal to each other. Likewise, if we define the length of this line 7PD as B, then the length of this side DC must be also equal to B. In the next step, we will join points P and B together by straight line. And we will join points P and C together by straight line. By joining points P and B, we created the right triangle, triangle PAB. Side AP is equal to side AB, and we have the rule that says that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides we have those two angles that are equal to each other because they are located in front of those two equal sides. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. We also know that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right triangle PAB? We have this angle equals to 90 degrees plus alpha, this is plus 2 alpha, so 90 degrees minus 2 alpha must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Here we subtract 90 degrees from the equation, and finally we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. Here we divide this equation by 2. And finally we get that alpha equals to 90 degrees over 2, that is 45 degrees. So this is angle alpha. It is equals to 45 degrees in its size. And this is also angle alpha that is equals to 45 degrees in its size. In the next step, we know that AD is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if you focus on the right side of the straight line AD at point P here, so here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. But before that, the right triangle PDC is also an isosceles triangle, and you know that any right triangle that is also an isosceles triangle, those two angles must be equal to 45 degrees in their sizes. Okay, we already found out that this is a right triangle that is isosceles triangle. We already found out that those two angles are equal to 45 degrees, so we don't have to repeat on the same proof that those two angles must be also equal to 45 degrees, because because it is exactly the same proof for this triangle. So this angle equals to 45 degrees in its side, and this angle also equals to 45 degrees in its size. Because of the fact that this is a right and associated triangle simultaneously. So in the next step, focus on the right side of the straight line AD at point P. So here the sum of the angles must be equal to 180 degrees according to the rule that states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AD at point P? We have those two angles. 45 degrees plus 45 degrees is 90 degrees. So 90 degrees plus the size of this third missing angle in total must be equal to 180 degrees according to rule 3. Therefore, this third missing angle must be equal to 90 degrees in its size. Why? Because 45 degrees plus 45 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles on the right side of the straight line AD at point P according to rule 3. So the big angle BPC is equal to 90 degrees in its size. So if we define this angle as alpha, that is to say angle QPC is equal to alpha, then this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. That is the size of the big angle BPC. So this angle must be equal to 90 degrees minus alpha. So in the right angle PCQ, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the small right triangle, before that, we know that BC is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if you focus on the left side of the straight line BC at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. So 90 degrees plus the size of this angle in total must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees in size, according to rule 3, of course. So, in the right triangle PBQ, this angle equals to 90 degrees minus alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we'll prove that the green right small triangle PBQ, this green triangle PBQ, is similar to the right big triangle PQC. So, why those two triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you prove that all the angles of the right big triangle PQC are correspondingly equal to all the angles of the right green small triangle PBQ. Therefore, those two right angles are similar to each other according to angle similarity also. I write it down. So if you found out that the big right triangle PQC is similar to the small green triangle BPQ. according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side PQ of the big right triangle PQC over side BQ of the small right triangle BPQ is equal to side QC of the big right triangle QCP over side PQ of the small right triangle PBQ. Actually, PQ is a common side that belongs to both triangles. PQ belongs to the green triangle PBQ, and PQ also belongs to the big right triangle PQC. So repeat again, we should find out that side PQ of the big right triangle PQC over side BQ of the small right triangle BQP is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PQB. So PQ is the missing side, so we leave it as it is. Over BQ. BQ equals to 4 units in itself according to what is given us the question. And it is equals to QC. QC is 9 over PQ. So we should find out that PQ over 4 equals to 9 over PQ. So here we cross multiply this equation, and we get that PQ times PQ, that is PQ square, is equal to 9 times 4, that is 36. So in total, we should find out that PQ square equals to 36. We take out of this equation, and we get that PQ equals to the square root of 36, that is 6. So we found out that the missing side PQ is equal to 6 units in its length. In the next step, we implement the Pythagoras theorem on the right big triangle, triangle PEQ. In this big right triangle PBC, in this big right triangle PBC, again, we implement the Pythagoras theorem on the big right triangle, triangle PBC. Here by PT is the progression for Pythagoras theorem. Side BC is the hypotenuse of the big right triangle PBC. So the square of the hypotenuse is BC square, and it must be equal to BP square plus PC square. Again, according to the Pythagoras theorem, on the big triangle PBC, the following equation is shown that BC square equals to BP square plus PC square. BP is 4 plus 9, that is 13. Therefore, BP square is 13 squared, that is 39. And it is equal to BF square. So, what is it's actually BP square. And again, according to the Pythagoras theorem, on the big right triangle PBC, BC square, that is the square of the hypotenuse, equals to BP square plus PC square. So BC square equals to BP square. So what is the value of BP square? If we focus on the right small triangle APB, according to the Pythagoras theorem, BP square equals to A square plus A square. A square plus A square is 2A square. So BP square equals to 2A square plus PC square. What is the value of PC square? We focus on the right triangle PDC. According to the Pythagoras theorem, on the right triangle PDC, PC square equals to B square plus B square, that is 2B square. So PC square equals to 2B square. Again, the hypotenuse of the big right triangle PBC is equal to 4 plus 9, that is 13, and BC square is 13 squared, that is 169. BC square equals to 169, and it is equal to 2A square plus 2B square, so 169 equals to 2, so we take out 2 as a common factor, so inside the brackets we have A square plus B square. So in total we should find out that 169 equals to 2 times A square plus B square. So here we divide this equation by 2. Finally get that A square plus B square equals to 100, again, A square plus B square equals to 169 over 2. Our mission, our task, is to find out the area of this trapezoid ABCD. Trapezoid ABCD consists of 3 components. The first component is the right triangle ABP, the second component is the right big triangle PBC, and the third component is this right triangle PDC. And you know that the area of trapezoid ABCD must be equal to the sum of the areas of the 3 components that it consists of. So the area of trapezoid ABCD is equal to the area of this small right triangle ABP plus the area of the second component that trapezoid ABCD consists of. The second component is the area of the big right triangle PQC. Plus the area of the first component that trapezoid ABCD consists of. The first component is the right triangle PDC, so it is plus the area of the right triangle PDC. So, again, the area of this trapezoid ABCD must be equal to the sum of the areas of the three components that it consists of. That is to say, the first component is the right triangle ABP, so it is the area of the right triangle APB plus the area of the second component that trapezoid ABCD consists of, and the second component is the right triangle PQE, the big right triangle PQC, plus the area of the first component that trapezoid ABCD consists of. The first component is the area of triangle PDC. So in total, the sum of those three areas must be equal to the area of trapezoid ABCD. So first of all, what is the area of this right triangle ABP? That is the first component of trapezoid ABCD. The area of this triangle ABP will be equal to the base of the triangle times the height over 2. The base is A, the height is also A, so it is A times A over 2. This is actually A squared over 2. And that's the area of the second component that trapezoid ABCD consists of. The second component is the big triangle PBC, so it is plus the area of the big triangle PBC So what is the area of this big right triangle PBC? The area of this big right triangle PBC is equals to the base of the big triangle PBC, that is actually BC, times the height. The height of this big triangle PBC is QP, so it is times QP. The base is BC times the height, that is QP over 2. So in total, we found out that the area of this big right triangle PBC is equals to the base BC times the height QP over 2, plus the area of the third component that trapezoid ABCD consists of. It is actually the area of the right triangle PDC. So what is the area of the right triangle PDC? It is equals to the base, that is B, times the height, that is also B, so it is B squared over 2. So in total, if you found out that the area of trapezoid ABCD is equal to A squared over 2 plus B squared over 2 is A squared plus B squared over 2. And we have the area of the big triangle P, the area of the big right triangle PBC. That's actually BC is 4 plus 9, that is 13, times QP. We already found out that QP equals to 659 over 2. Okay, so the area of trapezoid ABCD equals to A squared plus B squared over 2 plus 13 times 6 over 9. 6 over 13 times 6 over 2. 6 over 2 is 3, and 3 times 3 is 39. So total, if you found out that the area of trapezoid ABCD is equal to a squared plus b squared over 2 plus 39. This expression in total equals to 39. So the area of trapezoid ABCD is equal to a squared plus b squared over 2 plus 39. But we already found out that a squared plus b squared equals to 169 over 2. So we solve a squared plus b squared here by 169 over 2. And we have to divide it by 2 again, so it is 2 times 2 plus 39. So here we have 169 over 2 times 2, that is 4, plus 39. So here we will multiply 39 by 4 and then we divide it by 4 in order to become equal to this number, and we get that 39 times 4 is 156 divided by 4. So 169 plus 156 is 325 divided by 4. 325 over 4 is 81.25 square meters. So if you find out that the area of this trapezoid ABCD is equal to either 325 over 4 or 81.25 square meters. So we finish with the second question. In the next step, summarize the lecture. We'll start with the first question, of course. In the first question, our task is to find out the area of this rectangle ABCD. So in the moment we have a circle that is inscribed by rectangle ABCD. We know that this is called EF, that is equals to 12 units in its length. This is line segment FB, that is equals to 10 units in its length. Again, our mission is to find out the area of this rectangle ABCD. Okay. So, first of all, we define the width of rectangle ABCD as DA and the length as AB. Then we define the radius of this circle as R. So ON is the radius of the circle. ON is known to point N, that is the point of tendency of tangent AB with this circle. Therefore, for the term 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and M together by a straight line. OM is the radius of this circle, this equals to R. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Finally, also join points O and E together by a straight line. OE is the radius of the circle, that is equals to R. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay, so by doing this construction, we can do the small quadrangle DMOE. Inside the small quadrangle DMOE, we have 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of these 4 pieces again, into the must equal to 360 degrees. Therefore, this third missing element must be equal to 90 degrees. This third missing element must be equal to 90 degrees in its size. Likewise, in the lower quadrilateral, we have 3 right angles, and therefore this fourth missing element must be equal to 90 degrees according to the rule that I mentioned. So in total, we found out that the big angle MON is equal to already 80 degrees, and therefore the big angle MON is defined as a straight line. If MON is a straight line, then MN must be also a straight line. So MN is a straight line that touches the circle at 2 points M and N, and therefore it is a chord. But it is a chord that passes from point O, that is the center of the circle, and we know that any chord that passes from the center of the circle must be the diameter of the circle. So if you found out that MN is the diameter of the circle, in the next step we extended the radius EO by straight line until it touches the circle at this point N. So actually the radius EO is a straight line, and when you extend a straight line by straight line, the result must be a straight line. So EL is also a straight line that touches the circle at 2 points E and L. Therefore EL is a chord that passes from point O, and we know that any chord that passes from the center of the circle must be the diameter of the circle. So in conclusion, we can say that EL is also the diameter of the circle. Okay, EL is the diameter of the circle. EL is the diameter of the circle, and we have here, we know that EL is the diameter of the circle, so we can write here that EL is the diameter of the circle, but we already found out that MN is also the diameter of the circle, so we can add here that MN is also the diameter of the circle, and so EL is the diameter of the circle, and we know that in the big quadrilateral ADMN, we have 4 right angles, and therefore quadrilateral NADA, NADM is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DMNA, side MN must be equal to the opposite side AD. Okay, so here MN equals to AD, according to the rule that the opposite sides of a rectangle are equal to each other. But we know that DA is the width of a rectangle ACD, so we can write that DA is the width, and from this long equation, EL equals to the diameter equals to MN equals to DA equals to the width. We will derive that EL is the width of a rectangle ABCD. Okay. So in the next step, we join points N and F together by a straight line. By joining points N and F, we can add triangle LFE. Triangle LFE subtend on EL, that is the diameter of the circle, and therefore, according to rule 7, any triangle that subtends on the diameter of the circle must be equal to 90 degrees in its size. Therefore, this triangle LFE is equal to 90 degrees in its size, according to rule 7. So in the next step, we extended the diameter EL by straight line until it touches side CB of rectangle ABCD at this point. So we define the touching point of the extended diameter EL with this side CB. This point is point T. By doing this construction, we created the big quadrangle ETBA. Inside this quadrangle, big quadrangle, there are ETBA. We have 1, 2, 3 angles. The sum of 3 angles is 270 degrees. So 270 degrees plus the size of this 4 pieces again. In total, must equal to 360 degrees. According to rule, it said that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore, this 4 pieces again must be equal to 90 degrees and inside. So inside the big quadrangle ETBA, we have 4 angles. Therefore, according to rule 5, the big quadrangle ETBA is a rectangle. But we also know that the opposite sides of the rectangle are equal to each other. So in the big rectangle ETBA, side ET must be equal to the opposite side ET must be equal to the opposite side BA. So in the big rectangle ETBA, side ET must be equal to the opposite side BA. But BA is the diameter of the circle, BA is the length of rectangle ABCD. So we can write here that BA is the length, and for this equation ET equals to AB equals to the length. We derive that ET is also equals to the length, and we only found out that EL equals to the width. Our mission is to find out the area of this rectangle ABCD. Okay. So in the next step, actually we know that we defined this angle as angle alpha. So in the right small triangle EFL, this angle equals to alpha, this angle equals to 90 degrees, according to rule 7. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle ETG, this angle equals to alpha, this angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. It is very easy to say that the big right triangle ETG is similar to the small right triangle ELF according to angle similarity rule. That is to say, this is angle E, that is a common angle that belongs to both triangles. So I can find out that angle E equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So in total, we should find out that all the figures of the big right triangle ETG are correspondingly equal to all the figures of the right triangle ELF. Therefore, those two right triangles are similar to each other according to angle similarity rule. So again, we can find out that the big right triangle ETG is similar to the small right triangle ELF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive the side ET of the big right triangle ETG over the side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. So again, we derive that ET over EF is equal to EG over EL. ET is the missing side, so we leave it as it is, over EF. EF is 12, and it is equals to EG. EG in total equals to 12 plus 10, that is 22, over EL. EL is the missing side, so we leave it as it is. So in total, we should find out that ET over 12 equals to 22 over EL. So here we cross multiply this equation, and finally found out that ET times EL equals to 22 times 12. 22 times 12 is 264, so in total we should find out that ET times EL equals to 264. 264 times 12 is 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 264. But we already found out that ET is the left of rectangle ABCD and EL is the width. So we substitute ET by the left and EL by the width. So in total we found out that the left times the width of rectangle ABCD is equal to 264 square meters. The left times the width is the area of rectangle ABCD, and it is equal to 264 square meters inside. So we found out that the area of this rectangle ABCD is equal to 264 square meters. So we finished with the first question. In the next step I present to the second question and solve the second question of this lecture. In the second question, our mission is to find out the area of this trapezoid ABCD. We know that AB equals to AP, PD equals to DC, line segment BQ equals to 4 units in Islam, line segment QC equals to 9 units in Islam. Again, our mission, our task is to find out the area of this trapezoid ABCD. So AB equals to AP. So if we define AB as A, then AP must be also equal to A because they are equal to each other according to what is given in the question. Likewise, you know that PD equals to DC. So if PD is B, then DC must be also equal to B. In the next step, we join points P and P together by straight line. We join points P and C together by straight line. By joining points P, B and P, we create the right small triangle BAP. Those two sides are equal to each other, and we have the rule that says that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha according to the rule that I mentioned. We know that the sum of the angles in the triangle is equal to 180 degrees, and especially it is true in this right small triangle APP. Therefore, which angles we have in the small triangle APP? We have 90 degrees plus alpha that is 2 alpha. In total, it must be equal to 180 degrees. Here we subtract 90 degrees from this equation. If I found out that 2 alpha equals to 180 degrees minus 90 degrees, that is 90 degrees. Here we divided this equation by 2 and finally found out that alpha equals to 90 degrees over 2, that is 45 degrees. So those two angles are equal to 45 degrees. So we know that from this example we can derive that any right triangle that is also an associated triangle have always the same angles. One angle is a right angle and the two other angles must be equal to each other, and each of those angles must be equal to 45 degrees in size. And because of the fact that the right triangle ADP is also an associated triangle because PD equals to DC, therefore in a right and associated triangle, those two angles must be equal to 45 degrees in their sizes. Okay? So we know that AD is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if we focus on the right side of the straight line AD at point P, here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have is the right side of the straight line AD at point P. We have this angle that is 45 degrees plus this angle that is also 45 degrees. So plus, so the sum of those three angles must be equal to 180 degrees. So 45 degrees plus 45 degrees is 90 degrees, plus the size of this angle in total it must be equal to 180 degrees according to rule 3. Therefore, this missing angle, this actual angle BPC, must be equal to 90 degrees in size. Why? Because 45 degrees plus 45 degrees is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees according to rule 3. Okay, so the big angle BPC is a right angle, so if we define the size of this angle QPC as alpha, then this angle must equal to 90 degrees once alpha. Why? Because 90 degrees once alpha plus alpha is 90 degrees. That is the side of the big angle BPC. So this missing angle must be equal to 90 degrees once alpha. So in the right triangle PBQ, this angle equals to 90 degrees once alpha. This angle equals to 90 degrees. Therefore, this first missing angle must be equal to alpha. Why? Because alpha plus 90 degrees once alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in a triangle. Okay. Likewise, in the big right triangle QPC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees once alpha. Why? Because 90 degrees once alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in a triangle. In the next step, we prove that those two right triangles are similar to each other according to angle similarity rule. So, when those two right triangles are similar to each other, first of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are right angles, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees once alpha, therefore they are equal to each other. So if we prove that all the figures of the big right triangle APC are correspondingly equal to all the figures of the small triangle PQP. Therefore, those two right triangles are similar to each other according to angle similarity rule. So if we found out that the big right triangle PQC is similar to the small right triangle BPQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side PQ of the big right triangle PQC over side BC over side BQ of the small right triangle BQP is equal to side QC of the big right triangle PQC or side PQ of the small right triangle BQP. And again, we derive that BQ over QC equals to QC over PQ. PQ is the missing side of electricity over BQ. BQ is 4 and it is equals to QC. QC is 9 over PQ. So in total we found out that PQ over 4 equals to 9 over PQ. So here we cross multiply this equation and we found out that PQ squared equals to 4 times 9 is 36. Here we took out all of this equation and found out that PQ equals to the square root of 36, that is 6. So this is the missing side PQ, that is equals to 6 units in its length. In the next step we implemented the Pythagoras theorem on the big right triangle PBC. According to the Pythagoras theorem on the big right triangle PBC, BC squared, that is the square of the hypotenuse, must be equal to BP squared plus PC squared. Okay. Again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. The PQ over BQ equals to QC over PQ. PQ is the missing side, so electricity. BQ is 4, QC is 9 over PQ. So in total we found out that PQ over 4 equals to 9 over PQ. Here we cross multiply this equation and found out that PQ squared equals to 36. We took out of this equation and found out that PQ equals to the square root of 36, 36. So this inside PQ is 6 units. So in the next step, we implemented the Pythagoras theorem on the big right triangle PBC. According to the Pythagoras theorem on the big right triangle PBC, BC squared, that is the square of the hypotenuse, equals to BP squared plus PC squared. So again, the big right triangle PBC, according to the Pythagoras theorem, BC squared equals to BP squared plus PC squared. BC in total is 4 plus 9, that is 13. Therefore, BC squared is 13 squared, that is 169. And it is equals to BP squared. What is the value of BP squared? In the right triangle ABP, according to the Pythagoras theorem, A squared plus A squared equals to BP squared. So BP squared equals to 2A squared plus PC squared. PC squared, what is the value of PC squared? So if you focus on the right triangle PDC, PC squared equals to B squared plus B squared, that is 2B squared. So PC squared equals to 2B squared. So in total, I should find out 169 equals to 2A squared plus 2B squared. So we took 2 as a common factor out of those two expressions. So inside the brackets, we left only with A squared plus B squared equals to 169. Here we divided this equation by 2 and found out that A squared plus B squared equals to 169 over 2. Our mission is to find out the area of this trapezoid ABCD. The area of this trapezoid is equal to the sum of the components that trapezoid ABCD consists of. Trapezoid ABCD consists of this small right triangle ABP plus this big right triangle PBC plus this right triangle PDC. So the sum of the areas of those three components must be equal to the area of trapezoid ABCD. Again, the area of trapezoid ABCD must be equal to the sum of the areas of the three components that it consists of. That is to say, it is equal to the area of the small right triangle ABP plus the area of the big right triangle PBC plus the area of the right triangle PDC. Okay. So what is the area of this triangle ABP? The area of this triangle equals to the base times the height over 2. The base is AB, the height is AB over 2. So it is A times A over 2. That's actually A squared over 2 plus the area of the big triangle PBC. The area of this big triangle PBC is equal to the base, that is BC, times the height, that is QP over 2. Okay. So the area of the big triangle PBC equals to the base BC times the height, that is QP over 2. Plus the area of this right triangle PDC. The area of this right triangle ABC and PDC is equal to the base TC times the height DP over 2. So it is B times B over 2, that is B squared over 2. So the area of the right triangle PDC equals to B squared over 2. Okay, and we have here A squared over 2 plus B squared over 2 equals to A squared plus B squared over 2. Okay, we have here also BC in total is 13 times QP is 6 over 2. And 6 over 2 is 3, and 3 times 13 is 39. So here it is equal to 39. And we have here A squared plus B squared over 2. But we have only found out that A squared plus B squared is 169 over 2. So for example, A squared plus B squared here by 169 over 2, and you have to divide it by 2 again. So it is 169 over 2 times 2, that is 4, plus 39. So here we multiply this equation, we have here 2 times 2 is 4, so here we multiply 39 by 4, and then we divided it by 4 in order to come up to this number. So in total we should know that 169 plus 156 over 4 is their trapezoid ABCD. 169 plus 156 is 325 over 4. So if you know that the area of this trapezoid ABCD is equal to either 325 over 4 square units, so in terms of numbers, the area of this trapezoid ABCD is equal to 81.25 square units. Okay, thank you very much.